8.3, simplifying radical expression. You're going to find that a lot of this is the same thing as last time. Basically, we're going to be talking about product rule and quotient rule today, and I'm not even going to change it up. Technically, you can apply them to both radicals and rationals, as we have seen, right? Last couple examples in 8.2 were about converting from radical form into rational exponent, and then solving using product rule, right? It's the same thing. The only difference now is you can do that without converting to rationals. So if you prefer the radical form, it's going to be the same way. You just got to be careful about it, okay? So let's try this out. Let's just jump in. Product rule, remember it said, if you have the same base, then you can convert, or you can add the exponents, right? If you have the same base, you can add the exponents. The same goes for product rule, for a product rule when applied to radicals, as long as you have the same index. So it's slightly different, because if you remember, the base becomes the radicand. So this would have been 5 to the 1/2 times 5 to the, or 7 to the 1/2, right? We wouldn't be able to combine those until we actually found out what they were as 1/2. But when you have radicals of the same index, you can combine them under the radical. It works for real numbers. So you can combine them under the radical. And you'd get the square root of 35. And that's basically how the product rule works, okay? And the reason it works is because of PEMDAS. Basically, it doesn't violate PEMDAS. Let's try it again. So here we've got 2, square root of 2 times square root of 19. Since those are both square roots, and they're being multiplied, I can do that. I can put them under one radical, and I get the square root of 38. Okay, cool. Looking good. Let's keep going. Square root of 11 times the square root of p, that's going to be the square root of 11p. So you put them both under one radical. Can't actually multiply those out, but it might be convenient to only write one radical time. One more time. We have the square root of 11 times the square root of 7xyz. So many variables there. But again, the indices match. So I get 11 times 7 times x times y times z. Simplify what I can. You get 77xyz. Awesome. So that's basically the product rule. Notice there's some key things though. They have the same index and they are being multiplied. Product rule only applies to products. Okay, you must know what a product is. Product rule only applies to products. Let's do that with some higher powers now. Again, the indices match. Nowhere did I ever say it had to be a square. I just said the indices have to match. So I can throw them under one radical. One radical symbol. I get the cubed root of 36. Careful, that does not equal 6, right? The cubed root of 36 is not 6. 6 times 6. 6 squared is 36, right? The cubed root of 36 is 3.3019 ... Okay, so watch out for that. Watch your indices. Let's do another one. Same index. I can put it under one radical. 8y times 3r squared. Simplify what I can. I get the 4th root of 24yr squared. That's my final answer. Keep going. These indices also match, right? They also match. So I can put them under a 6, 10m to the 4th times 5m. Since everything's being multiplied, I can use that associative property, right? Multiply the coefficients. I'm sorry, not associative, commutative property. I get the 6th root of 50, and then I can apply the product rule within here. So m to the 4th plus m to, or times m to the 1st gives me m to the 5th. Fabuloso. Actually, yep, that power is higher, so I can't do anything there. That power is higher. That power is higher. Now, if as I was doing this, I noticed that maybe I got like a 12 right here, and that power was higher, then I could use my nth canceling property, right? I could say 6 of those will cancel with 6 of those, and I'll move on with life. Since 5 is lower than 6, I'm just going to leave it as it is, so that's inside. But if it was ever higher, I want to reduce it, okay? And we're going to talk about that again in just a second. But let's do this last one. Okay, you got the same base. We're good, right? So square root of 2 times 2. Nuh-uh, Miss K. You crazy. Don't do that. These indices are the same. Are not the same. So they cannot be combined. It doesn't matter if they have the same base. You can't change the index. Okay, you can't change the index. So if you have different indices, you now beg the question, what the heck are you supposed to write here, right? So you just can't do that one. It doesn't combine. That's as simple as it goes. Alright, hopefully that made sense. That's the product rule for squares and higher powers. Let's talk about the quotient rule now, which is virtually the same thing. It's virtually the same thing. We've seen this being used once or twice, actually quite a few times to be honest. But it basically says if you have two of the same power, the same index, then you can put them under one radical. Same thing as the product rule, it's just this time they're being divided. And it actually goes the other way as well. The other way I find is much more useful when simplifying. The only thing is if you have a variable down there in the denominator, b cannot equal 0, right? Because we can't divide by 0. So can't do it that way. But chances are you wouldn't have this set up if you got that anyways. So you probably won't have to worry about it in this class. So let's try it out. I've got this huge square root of 16/25. I will make that two different radicals. And then I find that it's very easy to simplify. I've got square root of 16 is 4. Square root of 25 is 5. 4/5. So basically it's like kind of like distribution property. Just distribute the radical. As long as those indices match. Right? As long as you want indice. Here we go with another one. I've got the square root of 7/36, which changes to the square root of 7. Square root of 7 over the square root of 36. Square root of 7 doesn't reduce very well, but the square root of 36, the principal root would be 6. And that's what we call a rational fraction. We're going to talk about that a lot in the next section. Alright, here we got the cubed root this time. Cubed root, not quite the squared root, but cubed root. But the product still applies, right? It still applies. Remember, this applies to any nth power. Hold on one second. Ooh, any nth power. So, we'll take the square root, or the cubed root of each. Cubed root and cubed root. Now, be careful. There's only one negative here. There's only one negative, so you don't need to make them both negative. In fact, you shouldn't make them both negative. If you do, then you end up canceling negatives and you're not at the right power. So I'm just going to stick it on the top. Okay, I'm going to stick it on the top. So the cubed root of -8, remember having a negative under a cube is not a problem because it's odd. So we get -2 over 5. We end up with -2/5. So watch out, that negative only needs to be applied once. But the idea is still the same. Quotient rule still applies. Let's try the third root here. Third root of 7th over third root 2/16, right? Split it up. The cubed root of 7 is definitely not anything. Let me just double check on the cubed root of 2/16. I want to say 6, yeah. So this would be the cubed root of 7 over 6. And yes, the cubed root of 7 is something, right? But it's such a long decimal and it's so ugly that even if you'd never be able to stop writing it. So let's just call it the cubed root of 7 and be most accurate, right? And we'll keep going. So now this one, quotient property says the 5th root of x over the 5th root of 32. The top one, I know nothing about x, so I'll just keep it the 5th root of x. 5th root of x. And then the 5th root of 32, that would be +2. Since it's an odd and it's positive. Last but not least, this negative is on the outside now, so it's going to stay on the outside. Cubed root of m to the 6th over the cubed root of 125. Okay, and this is what I was talking about in the last section. This 6 is bigger than this 3. So I can use my nth canceling rule, right? I can use my nth canceling rule and say I have the cubed root of m cubed, sorry, let's do m squared cubed. Those two cancel and I'm just left with m squared. Sorry. Okay. So you can see how the nth root power also applies here. And then this cubed root of that would be 5. So this would be over 5. And I've made a horrible boo-boo because I dropped my negative. So negative m to the 5th, m squared over 5 is our final answer. Alrighty, so quotient rule, product rule. You can split them up, you can put them together, right? So you can take two radicals, stick them together, or you can take one radical and make it two for either one, either the product rule or the quotient rule. Okay, the next thing we're going to talk about is super important. It's called simplifying radicals, okay? So you have a radical here, and this applies to any power, but we're going to start with square roots. Simplifying radicals. Radicals have a simplest form, regardless of what number sits underneath them. Now, if you have a perfect square, right, if you have a 4, or a 16, or a 9, or a 16, or a 25, right, then it makes sense, not 27, dyslexic moment, sorry, 25, then it just makes sense to convert them into whole numbers, right? That's the first thing. If you can convert it to a whole number, you need to convert it to a whole number, okay? Like, it's just not accepted. It's not even right to have it left as an unwhole, like, not even a whole number. However, there are so many numbers in between all of these that there's got to be another way to reduce them, okay? So the other numbers are not going to get left out as well. Let's take a look at 24. 24 has some hidden squares within it. It has some hidden squares within it, okay? So the idea here is we're going to take 24, that radicand right there, and we're going to take out all of these squares, okay? So we're going to remove all the squares. We're going to use this idea of product rule. So what I'm going to do is I'm going to break it down into any two factors that I see. Any two factors. Well, 24, I got 4 and 6, right? I got 4 and 6. I found a square. I found 4. But what I'm actually going to do is, in order to avoid this do I see a squares things, I'm just going to take it down to its prime factorization. Remember that from way back when? The prime factorization, where you split stuff up into primes? So I'm going to keep going. 4 and 4 goes, or 4 goes into 2 and 2. 3 goes into 2 and 3. Or 6 goes into 2 and 3. Okay? So I broke it down, right? I just keep breaking it down. It doesn't matter what factors you start with. You would have gotten the same thing had you started with 3 and 8. 3 and 8. Well, 3 is a prime, so that part's done. Break that down into 4 and 2. 2 is a prime, so that's done. Break that down into 2 and 2. I end up with the same 2, 2, 2, 3, 2, 2, 2, 3. Okay, so I'm just looking at the ends of my trees here. Either way, you get the same ends of the trees. Okay? Now what I want to do here is I want to look for any pairs. The pairs are going to show me my squares. Okay, so the pairs of 2s show me that I have a 4 in here. So this is a pair of 2s. And here's a pair of 2s. So I'm only going to work with the 4 and 6 version now. I'm going to go ahead and erase this so we don't have to do it twice. But I just wanted to show you either set of factors would have gotten you there. So now I see this pair of 2s, right? This pair of 2s. And what I'm going to do, what I'm really doing, is rewriting this as 2 squared times 2 times 3. So when I find a pair, what that means is I have a square, right? I have a square. The pair is the square. The pair is the square. Anyway, sorry about that. I got distracted. And then I can apply my nth power rule, right? Well, first I can apply my product rule. So now I've rewritten it like this. I can apply my product rule. Square root of 2 squared times square root of 2 times square root of 3, right? It says if I have one radical, I can split them up into as many radicals as I want, right? And then I can apply my nth power rule. So I have 2, those guys I'm going to squish back together into root 6. 2 root 6, okay? So I'm trying to break this down into things that can be squared. However many squareds I can find, those get to come out. That's what it is at the end of the day. Now, over the years, you've probably heard find the pairs. The pairs, if they have a date, they get to go outside, and if they don't, they have to stay underneath and all that jazz, and that's totally fine, right? Use whatever makes sense to you. But this is actually what's happening. You're splitting it up into squareds so that your nth power rules apply, okay? When we get to cubes, it's going to be the same thing, but with groups of 3, okay? So we're going to try another one in just a sec. So just hold on for just one. Okay, let's try another one. So we have square root of 108, right? Clearly not a perfect square by itself. We've got 144 and then 100, right? So somewhere in between 10 and 11, or sorry, 121 and 100. So somewhere in between 10 and 11. But that doesn't mean we can't pull out some stuff, right? We can pull out things from this 108. So let's start by breaking it down. Well, any two factors of 108. Any two factors, I believe, yep, 12 and 9. 12 and 9. Those are two factors. I'm going to write a heck smaller than that. 12 and 9. Neither one of those are primes, though, so I'm going to keep going down. There's 3 and 4. And 3 and 3. Well, those are both primes, and that one's a prime. That's good, but 4 is not a prime. I can break it down into 2 and 2. Alright, I found my prime factorization. Right? Now I want to rewrite this into pairs of squares. Pairs of squares. Here I have a pair, and here I have a pair, and then here I have a singleton. So I will write 2 squared, that's my pair of 2's, times 3 squared, that's my pair of 3's, and my last one is 3. Okay, now I'll use product rule. I don't honestly know why I changed colors. That says I can take all this huge radical symbol, and I can change it into 3 of them. Right? I change it into 2 squared. Can't write today for some reason. 2 squared times square root of 3 squared times square root of 3. And then I apply my nth power rule. So those two cancel, those two cancel. I have a 2 and a 3. That one doesn't have anything to cancel, right? He didn't have a pair, so he doesn't have a square, so he doesn't have anything to cancel. So this is just going to be square root of 3. And now multiply back together a little bit. 6 root 3 is my simplified form of the square root of 108. Okay? So you usually end up with 6 root 3, things like that. 2 root 6. We'll see how it plays the variables in just a sec. Let's try another one though. Square root of 10. Square root of 10. Okay, the only two non-prime factors, so not 1 and 10, but the only two other factors would be 5 and 2. And they're both prime, so I'm done. Okay. Now we have a problem. The problem is there are no pairs here, right? There's no way for me to take out pairs. So square root of 10 is as simplified as it goes. Square root of 10 is as simplified as it goes. Sometimes that happens. Just check the factors, right? Check the factors. And then lastly, we have so now we've got a cube. Remember, the cubed root of 16 does not mean 4. We are not dealing with a square this time. This time we are dealing with a cubed root, right? So let's start just by breaking it into its factored form. 4 and 4, right? Breaking this one into 2 and 2, 2 and 2. Now instead of looking for pairs with a square, I'm going to look for groups of 3. Groups of 3. So I have a group of 3 here. They do not have to come from the same tree. They do not have to come from the same tree. So I have a group of 3 here, and then I have a leftover one. So I'm going to rewrite the cubed root, the cubed root of 16 as the cubed root of 2 cubed times 2. Right, because I had a pair of 3's, that's 2 cubed times 2. And then I'll use my product rule that says I can split these up. And the nth canceling rule, and I end up with 2 root 2. I'm so sorry, cube there. I forgot cube there. And 2 cubed root 2. So cubed root of 16 is the same thing as 2 cubed root 2. Okay? Alrighty, it's not the same thing as 4. So hopefully that's making sense, right? Let's try another one. Here we've got negative on the outside, so negative stays on the outside. Right? And I've got the fourth root, I don't know what I'm doing. The fourth root of 162. Let's break down 162. I don't know about you, but 162 does not spark any immediate factors for me, right? I'm not like, oh, it's 16, 4 and 4, sweet. So what I'm going to do is just start by dividing by 2. I divide by 2, it's 81. Okay, there's 2 factors. 2 is a prime. 81, well, that sparks something. 9 and 9, right? 9 and 9. I can break that down in 3 and 3, 3 and 3. Okay. And I'm looking at the 4th root here, so I want to find pairs of 4. Here's a pair of 4. And that obviously doesn't have a pair of 4. I'm not going to consider the 9s or the 81 because I already broke those down, quote unquote, right? I only want to consider the primes. So I'm going to rewrite this as negative 4th root of, here's a pair of 4, so 3 to the 4th. Right, because the whole point is I want these guys to match. I want those to match to apply the nth root. And then I had that 2 left over. use product rule, negative 4th root of 3 to the 4th times the 4th root of 2. And I end up getting negative 3 because these guys cancel. Again, that was the whole point. I wanted to find that. I wanted to find that 4th they had in common. Times the 4th root 2 is my final answer. And that negative just kind of tagged along the whole time. There we go. Easy peasy lemon squeezy. Let's try one more. 40. Cubed root of 40. Let's do blue. Well, I see maybe 4 and 10. Again, it doesn't matter which ones you start with. If you started with 2 and 20, that would be fine too. You would end up getting the same primes. Prime factorizations are always unique. That breaks into 2 and 2. That one's 2 and 5. Now, before I go circling pairs here, let's go back and check that index. The cubed root of 40. I'm looking for pairs of 3. Pairs of 3. Alright, so I can rewrite this as the cubed root of 2 cubed times 5 because I have one pair of 3 2s. 3 2s, right? Use my product rule, the cubed root of 2 cubed times the cubed root of 5. And then my nth rule applies. I get 2 cubed root of 5. And I'm done. Alrighty. So that's how you simplify just number radical, okay? So you always have to check that index to make sure what size of pairs you're looking for. And then you can just use your nth canceling n power rules and index canceling the nth power, that idea to simplify those groups out, right? Simplify those groups out. Now let's take a look at it with variables. Variables will be the same thing, exactly the same. Remember I've said this before, variables are not special. They think they are, but they're not. They're really not that special. They are just numbers we don't know yet. They have to follow all the same rules, So let's try it, right? So I've got the square root of 16 here. Let's break 16 up first. Let's do what we know how we do. We have 16. I got 4 and 4. And 2 and 2. 2 and 2. Okay, cool. Broke that up. Now when I break up m cubed, well, the only thing I know about it is that it's m times itself 3 times. So the only products, or the only factors I know are m, and m, right? That is the quote-unquote prime factorization of a variable, okay? Not really prime because you don't know m is prime, but that is the prime factorization that we're going to go with. Okay, I am a squared radical, so I will be looking for pairs. 2 here, and 2 there with a leftover m. I always like to box the leftovers so I don't forget them. It's just a personal trait though. If you want to do that, you don't have to. Okay, so now I can rewrite this guy as the square root of 2 squared times 2 squared times m squared times m. Right? Use my product rule to say each of them gets their own radical. And then I can see that those are going to cancel, those are going to cancel, those are going to cancel. I get 2 times m. And the last one does not cancel because he's an extra. I run out of room, so I'm going to write that a little smaller. 2 times m times square root of m. I end up with 4m root m is my final answer. Alright, so notice it really wasn't that different from the variable, or when we added the variable, it wasn't that different. I just need to find pairs, or I just need to find groups that match the index. And those guys get them out. Let's try another one. This one's a little bigger, that's okay. 200 breaks down into 20 and 10, right? That would be 2 and 10. 10 breaks into 2 and 5. And 10 breaks into 2 and 5. Okay, cool. This one is a squared, so I'm also looking for pairs here. And there's a pair, and there's an extra 2. In red so you can see. Okay, cool. I've got 7 Ks. I'm not going to write them all. It means I have how many groups of 2? I have K squared times, let's see, I think 3 of them, because that would be 6. There's an extra 1, right? So that's what I end up getting. 8, I'd end up with 4 groups of 2, right? That's what I'd end up with. Okay, so I'm going to rewrite it over here. So I end up getting a very large radical of 2 squared, 5 squared, 2, 3k2. That's not going to fit there. And let's not put it there then. If you're going to be... My handwriting with this stylus is so large, it's so annoying sometimes. So let's do 2 squared, that's the first group, the 5 squared, and the 2. And then I've got 1, 2, 3 groups of k and 1 left over. And then 1, 2, 3, and 4 groups of p with none left over. I'm going to skip that step where we give them all their own radical, because I feel by now we got that. And then this, I'm actually going to go up. I hate doing this, but let's see. We got a 2 on the outside, a 5 on the outside, 3 k's on the outside. So 2, 5, k becomes k cubed, p to the 4th, square root of 2k. Ends up being our final answer. Oops, no it doesn't, because we can combine 2 and 5 to get 10. So even with large values, the concept is the same. All the squareds get to come out, right? And then you combine them together. They all cancel down to a single 2, 5, 3 k's, and 4 p's. And you get one of each of those on the outside. What doesn't have a square ends up staying inside the radical. Okay. Let's try another one. Maybe something with a few small numbers. Alright, cubed root this time, cubed root. So let's do -8. Let's split that into -1 and 8. We can start with that part. Then 2 and 4. And suddenly I can't write, which is really annoying. So 2 and 8. 2 and 4. And then 2 and 2. Alright. Next. You know what? I don't want to do it that way. Just kidding. Let's keep it negative. Split it into -2, +4. Split that into -2 and -2. Right? Since we're dealing with cubed root, I can tell that's going to be, that'll be nice and easy to read. Here, we got 4 x's, and we're looking for groups as well. Let's just write it out. X. Really? X, 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 and X, right? I've got 5 y's, so y, 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 and y, and y. Okay, must be careful. I'm no longer looking for pairs, right? I'm looking for groups of 3. So here's a group of 3. Here's a group of 3 and an extra one. And here's a group of 3 and an extra one, right? So this is going to reduce down. Those 3's are going to come on the outside. So -2 cubed times x cubed times x times y cubed times y times y. That's now all going to be under the radical. And that reduces down to -2 xy, right? Those guys get to come out. Who's left over? Xy squared. Alrighty. Now if you're understanding this, if you're definitely understanding this, you want to save space, you can skip this step where you write them out. You can also skip this step where you break it up using product rule. But you must know why you can do that, okay? You guys know that on my test, I ask questions about why you can do stuff and to explain properties and things like that. So if you just remember that I have to make groups of 3 and they get to come out, you better be able to tell me why. You need to tell me why, okay? That's part of this class, really understanding why you're doing stuff. That's like one of our objectives. So make sure that you really can tell me why. Let's keep going. Let's try another one. So we'll break down 32. This negative is just on the outside. So he's just going to chill on the outside. 32 is 2 times, no it's not. It's 2 times 16. And it's 2 times, well it's 4 times 4. And then 2, 2, 2, and 2. This guy I have 9 y's. So 1, 2, 3, 4, 5. Change my mind. I'm going to put it up here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. And I gotta be careful. I'm looking for groups of 4 here. So I've got a group of 4 right there, and an extra 2. And then group 1, 2, 3, 4 right there. 1, 2, 3, 4 right there, and an extra 1. So this becomes the 4th root, the negative 4th root of instead of 32y to the 9th, it's going to be 2 to the 4th times 2 times y to the 4th times y to the 4th, because I have 2 groups, right? Then an extra y. The 4ths get to come out, and I have 2y, so they become y squared. What's left over is the 4th root of 2y. And that's it. Alright, let's try this one now. Now, 9th root of 5 to the 6th. You may think there's nothing we can do because you've got 5 to the 6th, the smaller groups. But let's consider those rational exponents too. Maybe there's a way we can bring these down, right? So let's convert this to a rational real fast. We've got 5 to the 6 over 9, right? Remember, the index becomes the base, or sorry, the index becomes the denominator. And that is actually a reducible fraction. So we get 5 to the 2 over 3, right? And now if we convert it back, we get the cubed root of 5 squared, or the cubed root of 25. So it was reducible, right? It wasn't necessarily the same way we've been reducing things before, but always try to convert to a rational exponent and then see what happens, right? They're so interchangeable, you should always try to do that. The last 4 problems were all about the whole number ones, so those are easier. But let's try it one more time with this rational idea with a variable. Okay, so let's try a variable rational, and I'm going to pick a color eventually. So let's convert the 4th root of p squared into a rational fraction. So p becomes the base, 2 is the top, 4 is the bottom. And I notice, yes, that's not going to be a whole number, but it is going to reduce, right? 2/4 is the same thing as 1/2. So we end up getting the square root of p. And that's much easier to deal with than the 4th root of p squared, right? So watch out for that. If you've got a common factor, then it goes away, regardless of what it is. If it's a reducible fraction, if it's a whole number, basically you're looking for pairs of whole numbers or fourths or whatever, groups of whole numbers, or you can reduce a fraction down. Alright, the next topic I want to talk about is about things that don't really match at all. So remember, you've got 2 versions of product rule now. And the first one says you either have to have the same base if things are in exponent form. They must be both 5 to the 1/2 and 5 to the 1/3. That way you can multiply. Or they must have the same index, right? If they have the same index, you can put them under the same radical. However, sometimes you get stuff like this, where neither one is true. You have square root of 7 and the cubed root of 2. Right? So I don't have the same base. They're both not the same radicand. They're both not the same index, and so they're both not the same power, right? So it looks like I can't really do anything. However, we can come up with, or basically we can switch back and forth over and over again until we find a common index. So essentially we're going to do the same thing we would do if we were like adding them together with product rule, but we're going to find common index. That's our goal. Alright, this first one, I don't like this example. I'm going to change it on your notes. My apologies that I didn't do that before. It's actually going to be root 5 times the cubed root of 4. That should be the first thing that's on there. If it's not, then go ahead and cross it out and write it now. So let's see how that would work. There's nothing wrong with this problem. It just gets really big, and I just don't want to show you guys an example with a really big one. I want to show you a nice small one first. So right now, as it is, not the same base, right? Not the same radicand, 5 and 4. Not the same index, 2 and 3, not the same. So let's try converting them to rationals. So I have 5 to the 1/2 times 4 to the 1/3, right? 5 to the 1/2 times 4 to the 1/3. Now let's like kind of pretend we're going to add them. I very, very strongly use air quotes because we're not going to add them, right? It doesn't say add. It's not even the same base. Can't do that. So I'm just going to change them both so they have a common denominator. So it's going to be 5 and 4 still, but instead of 2 and 3, I'm going to make them both 6. So they're both 6, right? In order to get a 2 to a 6, I need to times it by 3, so I'll times the top by 3 as well. In order to get a 3 to a 6, I need to times it by 2, so I'll times the top as well. Now they have the same thing. Now I know everyone's tempted to go ahead and add them and say 20 to the 5 6. That's not true. Okay? But for now, we just wanted them to be the same. Next, let's convert them both back into radicals. So this first one is going to be a radicand of 5, and since the numerator to the third, it's going to be the 6th root of that. Right? So 3 stays a 3, the 6 becomes the radical part. Times the 6th root of 4 squared, right? And now they have the same index. Now I can apply product rule. So this would be the 6th root of 5 to the third times 4 squared. Well, 5 to the third is 125. And 4 squared is 16. 125 times 16 is 2,000. So we have the 6th root of 2,000. Let's see. That is not quite a whole number, but so we will leave it there. Let's reduce it a little bit. 2,000 divided by, well, 2 would be 1,000. Right. And then that looks like it would be 110. That's 10 and 10. That's 2 and 5, 2 and 5, 2 and 5. So it's 2 times 2 times 2 times 2 times 5 times 5 times 5. Yeah. And I don't see any group of 6s, so that will be our final answer. 6 root 2. Okay. So that's the basic breakdown, right? So you convert it once to find a common base, convert it back, and then solve like we just did up there. Let's try it again. So I've got cubed root of 7 squared. I can change that into 7 to the 2/3 times the 4th root of 3 cubed would be the, it would be 3 to the 3/4, right? Now I can find common base. Find a common base. That would be 12. So 7 times 3, and it would be 12 and 12. See, I had to multiply that one by 4, so 4 times 2 becomes 8. I had to multiply this one by 3. 3 times 3 is 9. Convert them back. You get the 12th root of 7 to the 8th. And the 12th root of 3 to the 9th. Put them under one radical, you get the 12th root of 7 to the 8th times 3 to the 9th. Or in other words, the 12th root of a very large number. And then the 12th root of that. Oops. We'll just leave it there. So that's pretty much as simplified as it's going to get. So not often is it helpful, but it does work, okay? You just have to find a common base, and then you can stick them back under one radical. Alright, last two things we're going to talk about are virtually the same thing. It's the Pythagorean theorem and the distance formula. So the Pythagorean theorem, you may have heard it. You may have seen it many, many a time. It is a exponential type of equation. I'm sorry, it's just a squared type of equation. A squared plus b squared equals c squared. And what it's talking about is when you have a right triangle. When you have a right triangle, right? A right triangle has a right angle somewhere in its angles, right? Of the three angles, one of them has to be right. That basically what this says, that the two sides attached to that angle, call them legs. When you square them and add them, square and then add, that is equal to the square of the third side. So that long side, we call it the hypotenuse. That's equal to the square of the third side. Okay. Since we're dealing with squares here, we'll do a Pythagorean theorem. So let's try seeing if we can use this formula. Remember, we got formulas. This actually means something, therefore it's a formula. Let's use this formula to see if we can figure out the missing side of these two triangles. So here we've got 4, 6, and C. They were even kind enough to tell us that this part was C, right? But we could tell that because it's the only side not attached to the right angle, right? It's the side across from that. So we know that this one is A and this one is B. A and B are totally interchangeable. Totally interchangeable. It does not matter which one you call A, which one you call B, as long as they are attached to that right angle. So let's go ahead and plug those in. I know my formula is A squared plus B squared equals C squared, right? And therefore, I can say that A is equal to 4 squared plus 6 squared is equal to C squared. Now be careful. This is not 10 squared. Pedos. Exponents come first. Exponents come first. Exponents come first. I'll say it one more time. Exponents come first. So this is 16 plus 36 is equal to C squared. And as you can see, 16 plus 36 is, not times, 52, not 100, right? That is not 10 squared. Okay, I got 52 for C squared, but since I need to find C, what I'm going to do now is take square root of both sides, right? And C will tell me, I'm going to take the principal root because it's a distance. Distance is the only thing that makes sense, only makes sense as a positive. So I have the square root. So C is equal to the square root of 52. Let's see if we can reduce that any. 52 divided by 2 is 26. That's 2 and 13, right? And those are my primes. So that's equal to 2 squared times 13. Or in other words, 4 root 13. C is equal to 4 root 13. Yes, you must reduce is the only answer I will accept. Alrighty, so that's one example of how to use Pythagorean theorem to find a missing side. Let's do it again and see if we can find a different missing side. This time the side that's missing is B, so I use my same formula, A squared plus B squared equals C squared. I plug in what I know. If this one's B, then this one must be A, right? Again, those are interchangeable, but that's okay. So I have 12 squared plus B squared is equal to 15 squared. That's 144 plus B squared is equal to, I want to say 125, but I'm probably wrong. 225, yep. 225. Subtract the 42 over 144, sorry, is equal to 81. Take the square root of both sides. Looks like the principal root, B, is equal to 9. I don't need to reduce because it's a whole number, right? We only need to reduce if it's not a whole number. A perfect square, pardon, perfect square. Alrighty, that's Pythagorean theorem. I have a feeling by now you probably got this one down, so I'm going to just kind of breeze over it. If you are still confused on that, email me. From this theorem comes another. From this theorem comes another. It's called the distance formula. From this formula comes another formula. It's called the distance formula. Looks a lot more like the radicals we have been working with, okay? So what this does is it allows us to find the distance between any 2 points on a graph. Any 2 points. It's very easy to find the distance between this point and that point because you can just count down the line, right? Or it's very easy to find the distance between this point and this point because you can just count over. But what about the distance between this point and this point? That's much harder to count, right? But notice that when I do that, what I've drawn here, what I've ended up drawing here, is a triangle. I ended up drawing a triangle, a right triangle. So the idea is, in order to find the green distance, you find the red distance and the orange distance, so this distance and this distance, and you essentially use Pythagorean theorem to solve, okay? This formula just lets you do it really fast. So we're going to do it both ways, and then we're going to use this formula to do it really fast. So let's start. Find the distance between the 2 points, 3, -4, and -5, 3. First with the Pythagorean theorem, and then with the distance formula. So let's cut this bad boy in half, so we can do both. This will be P, Pythagorean theorem, this will be distance formula, okay? First things first, let's start by plotting the points. So we've got out 3 and down 4. Out 3 and down 4. That's our first one. Let's do it. -5, +3. So back 5 and up 3. Right there. So that'll be our second point. Alrighty, and we want to find this pink distance. That pink distance there. Okay, so we want to find that pink distance, right? Let's start with Pythagorean theorem. Well, in order to use Pythagorean theorem, I'm going to need to draw a triangle. So I will draw the distance down. And I'm trying to use as many colors as I can so we can coordinate later. The distance over. Okay. So if this was a right triangle, right? The right angle would be right there. This side would be A. This side would be B. I'm not going to use that one. Oops. Side would be B, and then the pink side would be C, and we're solving for C, just like we did in the last problem, or the second to last problem. So let's solve for that. We know that the formula is a squared plus b squared is equal to c squared. What is the distance of A? Let's see, from 3 down to -4, that's going to be a distance of 7. So that's a distance of 7, right? And then from -5 all the way over to +3, that's a distance of 8, right? So 7 squared plus 8 squared is going to be equal to c squared. In other words, 49 plus 64 is equal to c squared. 49 plus 64 is equal to 113. And then the square root of 113 is going to be c. Let's see, 113, I want to say it's prime. Yeah, 113 is prime. So it doesn't have any factors, it can't be reduced anymore. Let's see if we can get the same thing using the distance formula. Okay, so the distance formula, how it goes is the square root, so it has a giant square root. It's a square root, not a cube root, of something squared. So we've got this thing being squared and that other thing being squared. Okay, we'll talk about what those things are in just like 10 seconds. So I've got two things being squared. That's the basic setup, right? And then when it looks at this, this is the same x2, x1, y2, y1 from way back when in chapter 3, very beginning of the year. And it just means the first x, second x, the first y, second y, right? So the 2 means second, y1 means the first, right? So if I look down at my 2 points, well, the first x is going to be this first x here. I'm sorry, second x, x2, sorry. It's going to be the second x here. So it'll be -5 minus, let's see, minus the first one, 3. And then the y's, 4 and 3, subtract the second one minus the first one. Now I gotta be super careful. I've got -4 there, so I want to make sure I minus the negative, right? Now let's simplify. Simplify a little bit. Start with the parentheses. -8 squared plus, see, that would be 7 squared. Oh, those numbers sound awfully familiar, right? They sound awfully familiar. And then I will square things. I get 64 plus 49. That sounds very familiar, right? And I get square root of 113 is equal to the distance, which is exactly the same as last time. So notice, these two are the same. All I've done is taken the square part and put it over here by making it a square root. This is A, and this is B. It's the same thing. It's the same thing. And distance formula, I didn't have to draw a graph and like count things and all sorts of nonsense. I could just plug in and go. I found it. But in other words, it's the same thing. So I hope you can see that. Let's use that distance formula to find two more distances. Two more distances here. I'm just going to cut this down the page because I'm having trouble seeing. Alright, I got a first point, a second point. With distance formula, I do not need to graph, so I can just go ahead and draw it. Or, sorry, use the distance formula. So D is equal to x2, that would be 3, minus x1 squared, plus y2, 7, minus y1, 2, squared. Now I solve. 3 minus 6, negative 3 squared. 7 minus 2, 5 squared. Didn't touch anything else until I got there, right? I didn't touch anything else except the parentheses, what I meant to say. Now I'll do the squared parts. 9 plus 25. The distance is the square root of 34. Square root of 34, or 34 is 2 times 17, so that's as reduced as it can go. Sweet. Let's do it again, one more time. So the distance is equal to the square root of x2, negative 2, minus x1 squared, plus y2, negative 12, minus y1 squared. Negative 2 minus 14, that's negative 16 squared. That would be negative 17 squared. Still being square rooted. A lot of people like to drop off the square root part because they're worried about the stuff inside, which is, I mean, you're not, no, just keep it there, okay? Don't drop it off. Because if you drop it off, you always forget to put it back. Everybody does. It's annoying. So 16 squared, negative 16 squared, that's 256. Plus 17 squared, negative 17 squared is 289, still square rooted. Add those together, get the square root of 545. And before we go on any further, please remember that when you square a negative, it becomes a positive. Okay, square a negative becomes a positive. 595, let's see. Oh, sorry, 545. 545. That breaks into 5 and 109. 109 divided by 3. Nope, 109 divided by 4. Let's see, 109 is not even. Doesn't sound like it's going to factor in anything. Yep, that is actually prime as well. So this is as simplified as it can go. 1 square root of 545. Alright, hopefully that answered some of your questions about distance formula, Pythagorean theorem, simplifying radicals, converting to exponents, and then simplifying. If not, shoot me an email, and I will see you in the